Thank you, everybody. Wonderful to be here. Quite honored to receive the award here for our humble little project. I want to just, first of all, just recognize just all of the wonderful, amazing projects that we're seeing here today. So great work to everyone else here. Diving right into it. The project was a little unusual for a university. Typically, when a project like this is done, the university will fund it, or they might do a design-build contract. In this case, it was a clinic care facility that was delivered through a public-private partnership, and that involved just everybody at the table from the get-go. And so we had a very tailored and fine-tuned building program and the functions of the building, and we had to really look at a couple of things in a little bit more particular way. We had to look at seismic a little bit more carefully because not only were we dealing with the developer, but the university, the owner, but also the users of the building. So it was really important for them to have a building that was resilient. Interestingly, this was an unlikely candidate for an award from the ACI, because originally there was a design competition and we'd submitted a steel project, which was, let me say, the default scheme. It was a sort of an office type building with light laboratory use. And when we started looking more closely at the steel alternative, we realized we had to deal with some issues in terms of the depth of the floor plate, for example, which would have exceeded 2.5 feet or more. We were looking particularly at height envelope that would, limit how tall the building could be. From a floor assembly, we were particularly concerned about vibrations and acoustics. And seismically, we thought, with the shear walls would do a better job for us in terms of the seismic objectives for the project. And ultimately, I'd say the architects were sort of keen on the concrete scheme for a couple of reasons. I think the aesthetics, and I think just the simplicity of the concrete minimizes a lot of the finished materials, and they were sort of interested in not just coating everything and hiding it under drop ceiling. So a lot of the areas are exposed, and of course you get this wonderful atrium. So what we did end up with, and it's always interesting for me to peel the skin back and look at buildings for what they truly are, in my opinion, but to look, beyond the skin deep and look at what we arrived at. I think we ended up with a fairly efficient floor plate, flat plates, no beams except for particular spots, and a shear wall seismic resisting system that was fairly easily integrated into the program spaces and allowed us to achieve the seismic objectives we were talking about. I'll talk about that in a little more detail. And importantly, I think here we're really dealing with trying to minimize the carbon impact of the project. What we were shooting for, and we've done this in the past, but we were shooting for getting up to 60 to 70% replacement in some of the foundation and retaining wall elements, and then when we're looking at the elevated slabs, looking at a little bit more cement content, really managing the entire process through so we can arrive at something that was significantly better than what you'd get just getting through it. An important factor here is concrete allowed us an extra floor. That was a big deal. To get an extra floor program in a building was really important for them, and that really, I think, ultimately drove the decision. A couple of things to point out. You saw that atrium. It's an amazing feature. It really speaks to, I think, sort of this idea of mental care, healthcare being kind of not sort of hidden away in some basement space, and really kind of elevating this idea of sort of walking into a place that kind of reflects this sort of open and sort of peaceful, graceful atmosphere as you walk in. And that was a big point for the architects. Again, we integrated a rooftop garden, which was quite serene and important again for the functioning to be able to have patients kind of access that space. And ultimately, from a structural standpoint, we were able to integrate all the shear walls in there in a way that didn't really impinge on circulation. One of the kind of interesting features of the project was a very large auditorium at the ground floor of the building, a teaching auditorium. And in order to accommodate that, we basically ended up with a series of transfer girders up here to pick up the loads that would have been transferred down on that column. Some of these things took some special attention. They're not always a typical component of building construction. So what you see here looks more like a bridge construction, but it uses multi-strand post-tensioning in combination with the mild reinforcement. And this is a model of that joint because, again, we're always driving for compactness and dimensions of structural elements. And so looking at the depths, even though this is, we're given grief for every one of those 54 inches of depth. And so it, couldn't have been 55. It had to, they would have liked to have it be 26. Didn't work quite that way, but they served the function ultimately. Were quite straightforward to build and integrated themselves neatly with the rest of the slab construction. As we do with projects in Berkeley and the Bay Area in California, where we're concerned about seismic risk and we're particularly close to fault when we have some very large motions to deal with, for special projects like this, we almost always get into detailed shaking simulations using nonlinear dynamic analysis. And that allows us to model every significant bit of the building. So that goes from the soil to the basement retaining structure to the shear walls and to the modeling of the reinforcements, so we can start to predict not only overall building movements, but also look at strain and look what's happening to maybe our reinforcement at various different levels of shaking. So we kind of are able to have the dialogue with the peer reviewers who are very keen on making sure that the limits are met and their buildings are going to perform. A simple shot at results. We're always looking at building drift, and we've heard a lot about what was learned from the damage, observed damage from the Turkey earthquake. And one of the things that emerged as I listened to some of the conversations was keeping drifts low is a big deal. And for us, that really amounts to having plenty of shear walls, having shear walls that are designed for the amount of shear that's expected to be resisted, not just a elastic estimate. And so with these, we were able to show that we achieved drifts roughly on the order of half of what the code would have required. It's a simple measure, but it has really profound consequences. One, obviously, the structure is protected. We know that this building, after a design basis earthquake, will be minimally damaged and will be easily repaired and reoccupied. But furthermore, the building is embedded and coated and clad with very, very expensive interior finishes, exterior finishes, and so they far outweigh the cost of the structure. And so we're really thinking about how to protect those elements. So keeping those drifts low is the sort of first line of defense. But we looked very carefully at attachment details and movement details. Those cladding panels in some cases are intended to allow for 3 inches of movement without breaking the water seal, which you can imagine drives the architecture detailing a little crazy. But it was really a really carefully detailed a project in order to achieve all of these things at once. And of course, construction is where all of the kind of theories and ideas come to meet reality. And we're always interested in learning a little bit, again, how our thinking about modeling and getting a detailed understanding of how to build things actually translates into construction. I just like to point out the orderliness of all of that construction. It's not easy to make it all sort of clean and nice and deal with all the MEP penetrations that often come into play. So this is a very important part of the work, is to follow through and follow up, and the contractor did a great job. So just to kind of conclude, we're really, I say, pushed to think deeply, but the systems themselves aren't so innovative, but I think the approach that we took to collaborate with the project architects and really trying to integrate those goals in a way that wasn't difficult or complicated. It was sort of part and parcel of the concrete construction system that we chose, and so that was really important. And we, I think, demonstrated some great results, particularly around seismic resilience, which is important, and we hope to see this building endure the inevitable. And ultimately, pushing the limits on carbon reduction on the concrete mixes tailored to the function use of the particular element was really a key piece, and I think, again, we made a nice impact on that. So with that, I'd like to just thank not only the ACI, but the dozens of collaborators we work with, from our own team at Tipping, and all the various folks that really helped us guide us along the way. So anyway, with that, thank you very much.